Okay, this is lesson 2.3. We are going to work on applying our slope, midpoint, and length formulas. So, step 1, does anybody remember what some of these formulas are? What formulas do we have? Yeah, we have the ones right there. We have a formula for slope, midpoint, and length. But we also have one for the standard equation of a line. What's that one? Nice. So we're going to just make a list of all of our formulas that are at our disposal so that we have the tools for our toolbox. So, formulas. The standard equation of a line is y equals mx plus b. Where m is slope and b is the y-intercept. Okay, we also have an equation for slope. Slope is represented in the equation of a line by m. So m equals rise over run. And when we have the coordinates of our points, we can determine what exactly the rise over run is. The rise is going to be the difference or the change in y, right? The change in a vertical. So it's the vertical distance from one point to the next. The run is x2 minus x1. That's the horizontal change, the difference between the horizontally the second point minus the first point. Good. We also have a formula for finding the midpoint. The midpoint of a line segment. The midpoint of a line segment is represented by the capital letter M. You can really give it whatever label you want, but M is found by taking the average of the 2 points that make the line segment. So x1 plus x2 divided by 2, and also for our y coordinate, y1 plus y2 divided by 2. And the last formula that we need to know that we will be working with today is the length formula. And I'm going to write it in two different ways. So we have a formula for the length of a line segment. Very basically, it's based on the Pythagorean Theorem. A squared plus b squared equals c squared. And when we're applying it to our uses, especially when we're on a graph, we draw the triangle, right? We make a right triangle underneath the line segment, and the hypotenuse of that right triangle will be the length of our line, and it has the length. So just to draw a picture off on the side, we're talking about a line segment that maybe looks like this, and we need to find the length of this. It's going to be the hypotenuse of a right triangle that we make, where one of the lengths is the change in x. So one of the lengths is the length that we're changing in x, which is x2 minus x1. And in our Pythagorean theorem, we're going to need to square that, plus the change in y, the vertical change, y2 minus y1 squared. And those are the formulas that are at our disposal, and we're going to figure out which one to use and when to use it and how to use it. Okay, we're also going to be applying what is called our 4-step problem solving. So every time we come to a question or a problem, we're going to be analyzing it based on these 4 steps. 1, understand the problem. 2, once we understand the problem, we can choose a strategy. So we're going to make a plan for what we're going to do. That's going to involve choosing which formulas to use and when. 3, once you've got your plan, once you've got your strategy, you can carry out the strategy. And once we've carried it out, we should come up with a solution, but we still need to reflect. Why do we need to reflect? We need to reflect to figure out if we actually have the right answer, if it makes sense, and if it actually answers the question that the problem was asking in the first place. Okay? So there's our 4-step problem solving. 1, understand the problem. 2, choose a strategy. 3, carry out the strategy. 4, okay, example 1 you have in front of you. It is a problem in which we need to find the shortest route. Find the shortest route. So we're talking in distances, right? The shortest route is going to be measured in distance. So we're talking about the length of a line segment. It's going to come in there somewhere, right? Let's read what we have. A ranger cabin is to be built in a flat wooded area near the straight road that connects the 2 campgrounds in a park. So we've got the 2 campgrounds, A and B, and we have that road that they want to, the road is there, and they want to build the cabin. A new side road will connect the cabin to the campground road. On the park map, the campgrounds have coordinates 2, 8.5, and B, 10, 4.5, and R, the site for the cabin, is at 6, 1.5. Each unit on the map grid represents 500 meters. So what are we trying to find out here? The question we need to answer in A, we need to find the route that minimizes the cost and number of trees that have to be cut down for the side road. We're going to draw a diagram of this route. So from the cabin site to the camp road, the road that connects the 2 campgrounds, what is the shortest distance from that road to the cabin site? What do we know about that distance or about that road? Since the area is level, it says it's flat, the shortest route for the side road is the cheapest and easiest to build. The shortest route from the ranger cabin to the campground road is perpendicular to that road. So the new road is going to meet the old road at a 90-degree angle. To describe the route of the side road and to calculate its length, we're going to find the point where the perpendicular from R meets the line segment AB. So we're going to need to use the coordinates of AB to calculate the slope of that line segment. And then we're going to find the slope of the line that meets it at a right angle. Okay? Right, the slope of the side road is going to be the negative reciprocal of the slope of AB. Then we're going to use that slope to determine an equation for the perpendicular line that passes through point R, okay, which also passes through point D on your picture. Good, so the first thing we need to do is calculate slope. How are we going to do that? We need to find the slope of AB. Okay, so we're going to find the slope of AB by using our slope formula. We've got rise over run, which is the change in y, that's y2 minus y1, over the change in x, which is x2 minus x1. And this is A. We're calculating the slope first of the line segment AB. Okay, our points A and B are given to us, so we can sub those in, making sure that y2 comes from B and x2 comes from B, okay? So we've got our y values, we got 4.5 minus y1, which is 8.5. That is the y coordinate of B. And then we have the x coordinate of B, which is 10, minus the x coordinate of A, which is 2. We can simplify this. 4.5 minus 8.5 is negative 4, and 10 minus 2 is 8. We can reduce this further. This is negative 1/2. So the slope of the line segment AB, the slope on the grid of the road that connects campsite A with campsite B, is negative 1/2. Since the slope of AB is negative 1/2, the slope of any line perpendicular to AB is going to be the negative reciprocal of that. So slide down here, we're going to have the slope of the line that is perpendicular, and that's going to equal the opposite reciprocal. So instead of a negative, I'm going to have a positive, and a reciprocal, we're going to flip this fraction. So the slope of that new line is 2. So now that we have the slope of both roads, and our goal is to find the point of intersection of the two roads, we first need to find the equation of both of those roads. So we're going to find the equation for AB, and we're going to find the equation for RD, where D is where the new road meets the old road, by substituting the slopes in and the coordinates of one point into y equals mx plus b. So first, for the road that already exists. For AB, we have a slope of negative 1/2, and we know that point A is on that road. So the point A is found at 2, 8.5. And we are going to sub that information into the standard equation for a line, y equals mx plus b, which is going to allow us to find out what b is, and then we'll have the equation for the line that represents the first road, the road that they already have. So here we go. Y, we're going to sub in 8.5. M, we know, is negative 1/2. X, we're going to sub in 2. Remember, this is multiplication, m times x, so we have 1/2 times 2, plus b. And we simply need to solve this for b. Negative 1/2 times 2 is negative 1. And now we can add 1 to both sides. We end up with b equals 9.5, which tells us that the equation of the line that represents the old road is y equals negative 1/2 x plus 9.5. So I'm going to give you the opportunity to do the exact same steps to find the equation of the line RD. You know the slope equals 2, and you know the point R, which is on RD, is given to us as 6, 1.5. Your job is to sub those points into the standard equation, y equals mx plus b, solve for b, and then down at the bottom you should have the equation for the line that represents the road that they're planning to build, the new road. Go ahead. Okay, hopefully you tried that on your own and you ended up with the two equations for lines that are shown on the board right now. Now what do we need to do? What are we going to use these equations for? Nadia, what are we going to use these two equations for? To find D. What is D? What is D? The point of intersection of these two lines, right? It's the place where the old road meets the new road. So wherever these guys hit, that's going to be point D. Okay, so if point D is where the lines meet, then that means that point D is on both of the lines. Does that make sense? So the point D, XY, will be on the old road, represented by this equation here, and it will be on the new road, represented by this equation here, which means that when they intersect, this y is equal to this y, which means that the rest of the equation is equal to each other as well. Okay? So this equals that, where the lines intersect. So all we have to do in the next step, set them equal to each other, solve for x, and use that x value to solve for y. Here we go. We have our two equations. We're going to set them equal to each other. So we're going to use negative 0.5 for the slope of the first line instead of, that's the same as negative a half, okay? Plus 9.5 equals 2x minus 10.5. Now I want to isolate my variable. That means I want to get all the x's on one side. It's also easier, often it's easier to move them to the left, but over here if I move them to the left, they're all going to be negative. So I'd rather move them to the right in this case. So I'm going to add 0.5x to both sides, leaving us with 9.5 equals 2.5x minus 10.5. Now what do I want to do, Mel? But yeah, I'm going to add 10.5 to both sides in order to get rid of it on the right side and isolate my variable. So we'll have 2.5x on the right, and we will have 20 on the left. Next step, Stephanie? Good. We're going to get both sides divided by 2.5 to isolate the x, to get x by itself. These guys cancel out, leaving us with x equals 20 over 2.5. You can put that in your calculator. You will get x equals 8. So that gives us the x-coordinate of D. That gives us the x-coordinate of the place where the two roads meet at a right angle. We still need the y-coordinate. So all we need to do is choose either one of our equations, either the road AB or the road RD, and see if we get y. If we want to double check our answer, we could put it into both and make sure that they come out with the same y value. We're just going to sub it into the equation for road AB. So we have y equals, I'm just going to sub that in there. We have y equals negative 0.5x plus 9.5. Sub in our x value of 8. Perform our algebra. 8 times negative 1/2 basically means you're cutting 8 in half, and then it's a negative. So that's negative 4 plus 9.5, which equals 5.5. So the point of intersection here, therefore, D is at 8, 5.5. But because it's a word problem, we would need to put our whole answer into a sentence here. So we would say, again, it would be a therefore statement, but we could say the shortest route, or the best route for the new road is from the cabin, which was R, 6, 1.5 to D. D is the point that we just found, 8, 5.5. The end. That's A. B, for example 1, asks us to find the length of the new road. So which formula, Amy, are we going to use to find the length of the new road? The length of RD is going to equal the square root of the change in X plus the change in Y squared. So we just simply sub in the points that we know. We have RD, the X values are 8 minus 6 squared plus our Y values, which is making sure we use the same one first, 5.5 minus 1.5 squared. We can reduce inside the brackets. 8 minus 6 is 2. 2 squared is 2 times 2, which is 4. And then we have 5.5 minus 1.5, which is 4. 4 squared is 16. Square root of 20. And we want to round to the nearest tenth. So we just throw that in our calculator. Square root of 20 is approximately 4.5. Therefore, the length of the new road is, and we're missing one more step because our grid information in the question told us that each square in the grid, each unit in the map represents 500 meters. So we have 4.5 times 500 meters, which equals 2250 meters, 2,250 meters. The length of the new road is 2,250 meters. Example number 2 wants us to determine a geometric property algebraically. So what is a geometric property? Well, a property is a characteristic or quality that is always true, and geometry has to do with shapes. So we'll take 2 examples here. This is a rectangle. A geometric property of a rectangle is that a rectangle contains 4 right angles. Another geometric property is that 2 of the sides are the same length and the other 2 opposite sides are the same length. A geometric property of an equilateral triangle is that all 3 sides are the same length and that all 3 angles inside the triangle are the same length. Those are just examples of geometric properties. In our example, we're dealing with a triangle, the triangle that is drawn for you on your handout. The vertices of triangle ABC are A, 5, 5, B, -3, -1, and C, 1, -3. We are to determine whether ABC is a right triangle. The first step in our problem solving strategy is to understand the problem. You have a drawing there, you have a diagram to help visualize the problem. And we need to determine whether that triangle is going to be a right triangle. Well, let's choose a strategy. If ABC is a right triangle, 2 of its sides must be perpendicular to each other. Let's go ahead and write that. If triangle ABC is a right triangle, then 2 of its sides will be perpendicular to each other. Another thing we need to make known here is we're working in a triangle. We're talking about right angle triangles, and we have a formula that applies to right angle formulas. We might need to know about the Pythagorean theorem for this. Okay, So in order to determine whether the two sides are perpendicular, this means two of the slopes, so there are 3 lines in the triangle, and 2 of their slopes must be opposite reciprocals. If they are, then we know that we are dealing with a right-angled triangle. Another strategy that we could use is to calculate the lengths of all 3 sides and check if those lengths satisfy the Pythagorean theorem to see if they do actually, if a squared plus b squared does equal c squared. If it does, we will know that we're working with a right-angled triangle. We're going to use 2 different methods. The first is going to be using the slopes of these 3 lines. Method 1. Slopes. So we need to find the slope of AB, the slope of BC, and the slope of CA. And if any of those slopes are perpendicular, we know we're working with a right-angled triangle. So the slope of AB, slope formula is y2 minus y1. That's the change in y, the difference in y's, and over top of the run, which is the difference in the x values. And we can sub in what we have here. We have -1. For our b is going to be our y2 and x2. So we have -1 minus 5 over -3 minus 5. This reduces to -6 over -8, which equals 3/4. So the slope of AB is positive 3/4. The slope of BC, we're going to be using the exact same formula, the change of y over the change in x. And we can sub in our known values from the points BC. We have 3 take away -1 over 1 take away -3. 3 plus 1, this is -3 plus 1 is -2. And in the denominator, we have 1 take away -3, which is 1 plus 3, which is 4. And this reduces to -1/2. So far, there is no connection here. The slope of AB is not the opposite reciprocal of BC. So let's try CA. Again, our formula for slope, change in y over the change in x. Sub in the values that we know, and I'm actually doing the slope of AC, so I'm using C as our second points and A as our y1 and x1. -3 minus 5 in the numerator, and in the denominator, our run is 1 take away 5. This reduces to -8 over -4, which is 2. And now we should be able to see that since the slopes of BC and AC are opposite reciprocals, triangle ACB is a right triangle. So since the slope of AB and the slope of AC are opposite reciprocals, triangle, well, let's say this, angle, so what is our right angle? Angle C is our right angle because that's the length that is in common here. That's the point that's in common between these two line segments. So angle ACB is a right angle, and triangle ABC is a right triangle. In method 2, using method 2, we're going to use Pythagoras theorem, the Pythagorean theorem. So we know that in the Pythagorean theorem, a squared plus b squared equals c squared. And this is only true in right triangles. So if we had the points A, B, C, kind of like we do in our triangle, then the length A squared plus the length of B squared should be equal, well, must be equal if it's a right angle triangle, to the length of C squared. So that's what we're going to be looking for. We're going to be finding the length of the side B, which extends from A to C, finding the length A, which extends from B to C, and finding the length C, which extends from A to B. And we'll sub those values into the Pythagorean theorem. If it comes out equal, we know we're working within a right angle triangle. So here we go. First, the line segment AB. Using our distance formula, we know that this is x1, the change in x, so the horizontal distance, that's x2 minus x1 squared, plus y2 minus y1 squared. And for the points A and B, we can sub in the values that we have under the square root, also called a radical. So under the radical, we have -3 minus 5 squared plus, in a bracket, -1 minus 5 squared. Keep our radical and reduce our brackets. This becomes -8 squared plus -6 squared. And -8 times -8 is +64. 6 squared, -6 squared is 36. The length AB then equals the square root of 100, which we know is 10. I'm going to use the exact same strategy to find the lengths of the line segment BC and the length of the line segment AC. So I'm going to leave this top note here. I'm going to clear the rest and continue on. Maybe even I'll leave my radicals. Nope. Okay. The length of the line segment BC. Is equal to 1 minus -3 squared plus -3 minus -1 squared. Under the radical then we have 4 squared, and -3 plus 1, that's going to be -2 squared. Which reduces to 16 plus 4, which is the square root of 20. And we want an exact value, so we actually have to leave this answer as the square root of 20. If we round it to decimals, then when we use it again in the Pythagorean theorem, it won't come out quite right because we would have lost information in rounding. All right, so there's our length of BC. Let's go again for AC, the line segment AC. Using our formula for the length of a line segment, we can sub in our values again. We've got 1 minus 5 squared plus -3 minus 5 squared. This bracket reduces to -4 squared plus -8 squared. Here we're looking at 16 plus 64, which equals the square root of 80. And again, the square root of 80 is a decimal, in which case we would have to round, and we don't want to round, we want an exact value. So we have, with our three lengths, we have found out that AB is equal to 10 units. We have found out that BC is equal to the square root of 20 units. And we have found out that AC is equal to the square root of 80 units. Now we have already found out using method 1 that this is going to be a right angle triangle, but we're going to confirm it here using the Pythagorean theorem, which is a squared plus b squared equals c squared. So we need to know which side is the longest side in order to know how to put this into our equation. We need to check the square. If the square of the longest side equals the sum of the squares of the two shorter sides. Well, AB here is our longest side because 10 was the square root of 100, which is greater than BC or AC, okay? And so we can sub that in. We're going to check to see if AB squared equals BC squared plus AC squared. Well, AB squared is 10 squared. BC is 20, and we're going to have that square root of 20 squared. AC is the square root of 80, and we're going to have that squared. 10 squared is quite simple. 10 times 10 is 100. These guys are actually just as easy. Squaring and taking away the square root are opposite operations. Okay, so the square rooting this 20 and squaring are opposite operations. So if we do one and we do the other, we're just going to be left with the value that's under the radical. So if we take the square root of 20 and then square it, we'll be right back up at 20. And so with the square root of 80, if we take the square root of 80 and then we squared it, we'd be right back up at 80. 100 equals 20 plus 80. That is a true statement, which tells us that the Pythagorean relationship does apply. Since the Pythagorean relationship applies, triangle ABC is a right triangle. If it were not a right triangle, then the Pythagorean theorem would not apply. There's often more than one way to solve a problem in analytic geometry. So this is two ways that we used. They both worked. And from here on out, it's just more tools for your toolbox, determining which strategy you should use for any given problem. In example 3, we'll be using the same formulas that we've been using throughout this lesson and the unit to compare a median to a hypotenuse. So we're using the same triangle that we used in example 2, triangle ABC with a right angle at C. Angle BCA then is a right angle. And we need to show that the median from the right angle of the triangle in example 2 is half as long as the hypotenuse. So the median that comes from the right angle is going to hit AB somewhere around there. And our goal is to show that the length of this median is half the length of AB. So there's a couple things we need to know in order to figure this out. We need to know the length of the hypotenuse from A to B, which we already figured out in the previous example. And we also need to know the length of the median from the right angle to the hypotenuse. In order to find out that length, we're going to need to find this point, which happens to be the midpoint of AB, because a median stretches from one vertex to the midpoint of the opposite side. So by definition, the median will hit AB at its midpoint, which means this length will be the same as that length. Okay? We already know that C is the vertex with the right angle, AB is the hypotenuse, so now we need to determine the midpoint of AB. Once we determine the midpoint of AB, we will be able to determine the length of the median. Then we can compare this length to the length of AB and see if this length is indeed half the length of AB. Okay, carrying out our strategy, we're going to let D be the midpoint of the length AB. You can give that point any name you like, but let's calculate D. D is the average of A and B, right? So we have x1 plus x2 over 2, and our y-coordinate is going to be y1 plus y2 over 2, and this should be a big bracket. Let's sub in the points that we know. Our two x values are 5 and negative 3. So 5 plus negative 3 is the same as 5 minus 3 over 2. And we have our y values. That's 5 plus negative 1. That's the same as 5 minus 1 over 2. We can reduce this. 5 take away 3 is 2. Divided by 2 is 1. And 5 take away 1 is 4. Divided by 2 is 2. So here we have the midpoint. Point D is found at 1, 2. I'm going to add that to my diagram. Good. Now the endpoints of the median are C and D. So we can go ahead and use our formula for the length of a line segment in order to find the length of the median, CD. It equals, here's our length formula, right? We have the change in our run, that's x2 minus x1 squared, plus the change in our rise, that's y2 minus y1 squared. Sub in the values that we know, 1 minus 1 squared plus 2 minus negative 3 squared. 1 minus 1 is 0. 0 squared is 0. 0 times 0. 2 plus 3 is 5. Squared is 25. This is the square root of 25, which is 5. As shown in example 2, substituting the coordinates A, 5, 5, and B, negative 3, negative 1 into the length formula tells us that AB, so this is CD, the median, right, has a length of 5, and AB, which we already found out before, has a length of 10. Since CD equals AB divided by 2, 5 equals 10 divided by 2, the median from the right angle is half the length of the hypotenuse. So here we used our points AB to find the midpoint D, then we used the midpoint D and the point C to find the length of the median, and then we tested to see whether or not it was indeed half the length of the hypotenuse, and it is. So on our diagram, I could even show that this line, this median, has the same length as BD and the same length as DA. That's it. You have your homework sheet. Go ahead and try those problems and come to class with questions.